In previous video, we took a look at transformations, in particular shifts. And so just recall that with shifts, we add or subtract a constant. And this is going to move the graph either up or down if it's on the outside, or to the left or right if we're adding or subtracting on the inside. And in this example, in this video, we're going to take a look at scalings. And with scalings, this is going to be when we multiply or divide by a positive constant. So for example, if we were to multiply outside by a positive constant a, then again, outside transformation is a vertical transformation, and in this case, that's going to be a scaling. And so what that means is that the graph is stretched or compressed depending on the value away or towards the x-axis. And if this transformation, this multiplication by a, occurs on the inside, then we get a horizontal scaling. Okay, and here we need to be careful that when we multiply by a on the inside, this means we're actually going to scale the graph by a factor of 1 over a. So just like shifts, these scalings behave maybe a little bit counterintuitively from what we might expect. And so the graph in this case is stretched or compressed from the y-axis. And we'll take a look at an example to illustrate this in a second, but to point out, with horizontal changes, we're going to get a stretch when the value of a is a positive number, which is less than 1. And we're going to get a compression when actually the value of a is bigger than 1, okay, which might be a little counterintuitive. For vertical shifts or vertical scalings, this behaves as we would expect. We get a stretch when the value of a is bigger than 1, and we get a compression when this positive value is less than 1. So let's take a look at an example. Okay, and so now in this example, we start with a graph of a function y equals f of x, which I've recreated in part A and B. And we're going to apply in a transformation in parts A and B. So in part A, the transformation is we're multiplying by a factor of 2 on the outside. And so when we apply this change on the outside, that means we have a vertical transformation. So outside equals vertical. And in this case, because we're multiplying, this is going to be a vertical scaling by a factor of 2. And so what that means is each point on the graph is going to get moved away from the x-axis in a vertical direction by a factor of 2. So it's going to wind up 2 times as far away from the x-axis. So this point at minus 2, 6 is now going to, it is 6 units away from the x-axis. It's now going to wind up twice as far away, namely it's going to wind up 12 units above the x-axis. So this point started at minus 2, 6, and now we scale its y-coordinate by 2 by a factor of 2. And so it winds up at minus 2, 12, way up here. The point at minus 1, 4, it has a vertical distance of 4 units, and now it's going to have a vertical distance of 8 units away from the x-axis. So this point it's going to wind up at minus 1, 4 times 2, in other words, minus 1, 8 over here. And we do this for the other point. So this point at 1, 4 winds up at 1, 8. And this point over here at 3 minus 2, it's going to wind up twice as far away from the x-axis. So it was 2 units below the x-axis. Now it gets stretched and winds up at 4 units below the x-axis. So this point gets moved down to 3 minus 4 over there. So in the end, if we connect these points, our graph looks like this. Okay, and so notice that the x-intercept actually doesn't move. It is 0 units away, and it stays 0 units away. All of the other points get stretched twice as far. And so cleaning this graph up in A, here's the finished product. This graph gets stretched away from the x-axis in the vertical direction by a factor of 2. In part B, we now are multiplying by a factor of 2, but this multiplication is happening on the inside. So this inside change is a horizontal change. And since we're multiplying by 2, this is going to be a horizontal scaling by a factor not of 2, but of 1 over 2. So this is going to be actually a compression, meaning that it is going to get squeezed closer to the y-axis. So this is going to be a horizontal compression. So each of these points, for example, the point at minus 2, 6, it gets moved halfway closer towards the y-axis. So it gets compressed by a factor of 1/2. And so it's going to wind up over here at minus 1, 6. So we started at the point minus 2, 6. It gets compressed by a factor of 1/2. So it winds up at minus 1, 6 over here. And we do this for every other point. So for example, this last point at 3 minus 2, we compress the x-coordinate by a factor of 1/2, so it's going to wind up at 3/2 minus 2. So this point over here at 3 minus 2 gets moved halfway towards the y-axis. It winds up at 3/2 minus 2. And we do this for every other point. So this point at minus 1, 4, it winds up halfway closer to the y-axis at minus 1/2, 4. And this point at 1, 4 gets moved halfway closer to the y-axis over here. It winds up going to 1/2, 4. And so we get the following graph here. So if I draw this graph, say in red, that's the result. And so we've squeezed this graph closer to the y-axis, and this point, the y-intercept, since it starts 0 units from the y-axis, it doesn't get moved at all. All the other points get squeezed halfway closer to the y-axis. And getting rid of the original graph here would be the end result of a horizontal scaling by 1/2.